Welcome to the miscellaneous topics section of modern physics. This is the last section in your textbook before the appendix. There are two projects in this section, modeling semiconductors, which we'll be doing today, and modeling the universe, which we will do next class. These are similar to the projects that we do in lab, and I'm going to do some of it for you. You're going to finish both of these for homework. And I'll be reading some of it as we go through, but I might skip over some parts, so you'll need to finish reading it on your own and answer any of the questions which we don't get to together. So we're starting on page 3 for modeling semiconductors, so you can read along with me. In a gas where interatomic distances are large, the energy levels of one gas atom are not altered by the presence of the other gas atoms. Thus, you can think of each atom as a separate entity. A simplified energy level diagram for two gas atoms would look like this. So we have one atom here and one atom here. Then we have the energy levels, which are not influenced by the presence of the other atom. However, in a solid, the atoms are close enough together that they directly influence each other's energy levels. For example, in a hypothetical two-atom solid, which would be a pretty small solid, the energy levels look like this. The splitting in the energy levels occurs because an odd wave function, positive in one well and negative in the other, has a different energy than an even wave function, which is positive in both wells. If we were to look at realistic solids with more than just a handful of atoms, this discrete splitting into two levels, like we have here, becomes a continuous blurring of energy levels into energy bands. So we have one energy band here and another energy band here, and between them, this distance is the band gap. Thus, the allowed energy levels for the electrons in solids are actually continuous bands separated by finite gaps in energy. The size of the band gap between the highest filled energy band, which is the valence band, and the lowest unfilled energy band, the conduction band. So since we only have two bands here, this would be the valence band if it's the highest filled energy band, and the lowest unfilled energy band is the conduction band. The size between these two, the band gap, is of crucial importance in determining the solid's properties. Now we're on page 4. For example, if this band gap is large, that's here, a few electron volts, electrons in the valence band will not be able to easily jump into the conduction band. So we have electrons here, it's a large jump for them to get up into the conduction band, and because it's so large, it's unlikely to happen, and the solid will be an electrical insulator. So we have an insulator here with a large band gap. If the gap is basically non-existent, that's here, the electrons have free access to the conduction band, and the solid is a conductor. If the gap is small, near 1 electron volt, the solid has a rich variety of intermediate properties that make it particularly intriguing. These materials are intrinsic semiconductors. The 3 possibilities are listed below. Okay, we're going to look at two types of semiconductors. We're going to look at intrinsic semiconductors here, and later on in this project, we'll look at doped semiconductors. For intrinsic semiconductors, we are only looking at one element or compound. For doped semiconductors, there are impurities which are added. So now it's time in part 2 for the tail of the little electron that longs to be free. Imagine an electron in the valence band of a semiconductor. This electron is bound to its parent atom, but longs to be free to roam the entire solid. If only it could jump up to the conduction band. If it could, it would no longer be bound to any one atom, but rather it would be free to flow wherever forces take it in the solid. In other words, it could be part of a current. But where will it get the energy needed to make this jump? From the random thermal vibrations of the solid. In general, the relative probability of acquiring an amount of energy E from the thermal energy available in materials is given by the Boltzmann factor, where E is the energy acquired, T is the temperature in Kelvin, and K is Boltzmann's constant. For quantum mechanical reasons that we will gloss over, the effective energy needed to jump the gap is only about half of the actual band gap, and even this factor of 1/2 depends on the precise manufacturing of the semiconductor. Thus, the probability of an electron jumping from the valence band to the conduction band is what we have here with E replaced by E gap over 2, where E gap is the band gap energy, which we saw back here. For an insulator, we're going to say E gap is about 4 electron volts at room temperature, which is 293 Kelvin. The probability is about 10 to the negative 35th. So the little electron that longs to be free better get used to being totally bound to its parent atom. For a semiconductor with a band gap of 1 electron volt, the odds are much better. So at room temperature, we get 10 to the negative 9th. You may think that a 1 in a billion chance is pretty small odds, but remember there are about 10 to the 22 atoms in a single gram of silicon. At these odds, quite a few electrons will win the lottery and be free. Of course, in a conductor, every atom contributes a free electron, so although an intrinsic semiconductor will conduct current, its conductivity is quite a bit less than a typical metal. One interesting property of intrinsic semiconductors in contrast to conductors is their very strong temperature dependence. Semiconductors become exponentially more conductive with increasing temperature, while conductors typically become linearly less conductive with temperature. This allows semiconductors to be very effective at thermistors. For example, over a temperature range from 0 degrees Celsius to 100 degrees Celsius, the current in a semiconductor will increase by a factor of 0 degrees Celsius is 273 Kelvin, 100 degrees Celsius is 373 Kelvin. If we take the ratio here, we get 300. This enormous change in current can be easily measured, allowing a very precise temperature determination. One final feature of intrinsic semiconductors is the concept of a hole. And if I haven't said so already, for intrinsic semiconductors, the number of holes is equal to the number of electrons. We have the conduction band here and the valence band here. This is a before picture and this is an after picture. When an electron jumps from the valence to the conduction band, a process termed thermal generation, so we have an electron from our valence band, which is jumping up to the conduction band. So now we have an electron here, and what's left behind here is a hole. So it leaves behind a positively charged atom. Valence electrons from other atoms can then move into the vacancy or the hole in the first atom. This process will continue with the hole gradually moving through the solid. So here they have the hole current going this way. So if you have an electron here, which goes and fills the hole, now we have a hole here. Now this electron can fill this hole, now the hole is here. And so it's as if we have a hole moving this way. Now let's finish reading what we have here. This process will continue with the hole gradually moving through the solid. In fact, the motion of the hole is indistinguishable from the motion of an actual positive charge carrier. So it doesn't matter that it is a hole. You can think about it as being an actual positive charge carrier. This process does not occur in conductors because in a conductor, all of the atoms are missing electrons, and thus all of the atoms have the same positive charge. In the graphic below, the black dots represent electrons and the white dots are holes. Notice that the electron current and the hole current are always in opposite directions. Okay, so if we have positive charge going this way, then the hole is moving this way and the electron is moving the other way. Okay, now on page 6, we have some problems to solve. Recombination occurs when a freely moving electron meets a freely moving hole. The energy released at recombination when an electron falls into a hole, so that would be like the picture we have here. If this electron moving this way meets up with another hole moving this way, the electron can drop back down and fill the hole. That's recombination. The energy released at recombination when the electron falls into the hole is normally absorbed by neighboring atoms, but it is possible to construct a device in which this energy is released as a photon with energy closely matching the band gap energy. This device is a light-emitting diode, or LED. Photovoltaic cells are, in essence, this process in reverse, in which an incoming photon creates an electron and hole current. Okay, so now we have 4 different parts for problem 1 to solve on this page. I'm going to do part A and B for you, and then you can do part C and D for homework. Going back to page 4, they gave us an equation here. We have the probability is e to the negative e gap divided by 2kt. Now be careful here. The k that we're using, they gave the value for that here. That's Boltzmann's constant. That's also in the appendix. And that is 8.617 times 10 to the negative 5th electron volts per Kelvin. Let's write that down. 8.617 times 10 to the negative 5th electron volts per Kelvin. Okay, so that's not the only constant that we use the letter K for. And in this project, we're actually going to be using Gauss's law also. And remember that when we're doing things with the electric field and electric forces, that K is Coulomb's constant. Okay, so make sure you keep those straight. In question 1, part A, we have a 5-gram crystal of pure germanium, and the gap, the energy gap, is 0.7 electron volts. At room temperature, we want to determine the average number of mobile electrons. Okay, now here's where it gets just a little bit tricky because they didn't actually give us everything that we need to know in order to answer this question. You can read about semiconductors on the Hyperphysics website. They have some good information there, and also I think it's in chapter 9 of OpenStax Physics. You can read about semiconductors also. Okay, so what we need to know is we can take this probability, and from it we can find the density of conduction electrons. So the density of conduction electrons, which we're going to call N sub C, is approximately equal to, I'm going to call this C for a constant. This constant actually depends on temperature though. So it's some constant C times e to the negative e gap over 2kt. Okay, where C is equal to 4.83 times 10 to the 21st with some units which I'm going to ignore, times T to the 3/2. Okay, so this constant C depends on the temperature, but I don't want to solve the problem this way. So later on here, I'm looking at what temperature will the number of mobile charge carriers be twice the number, and I don't want to have to use a different value for C down here. So I'm going to say as long as T doesn't change much, so if T is roughly equal to 1093 Kelvin, and it's not changing that much. So this is kind of like when we say when little g is equal to 9.81 meters per second squared. That's true at sea level, but as long as you're not going to the top of Mount Everest, as long as you're staying pretty close to sea level, you can use 9.81. So we're going to do something similar here. This C actually depends on temperature, but that would make the problem much harder to solve. So we're just going to say if C is approximately 293 Kelvin, then we get 2.42 times 10 to the 25th electrons per meter cubed. So you can use this in our project today. Okay, but if you wanted to answer other questions where the temperature is changing, you'd have to use this. Okay, and you can read about this on hyperphysics. Okay, so now we're going to put that in to our formula here. So this is 2.42 times 10 to the 25th electrons per meter cubed, since that's the density of conduction electrons. I'm going to leave the units out for now, though. Okay, now this is E to the minus. E gap is 0.7 electron volts divided by 2 Boltzmann's constant, which is 8.617 times 10 to the negative 5th electron volts per Kelvin. And then we're at a temperature of 293 Kelvin. So that cancels out. And then I have electron volts here and here, so that cancels out. And for this, I get altogether 2.31 times 10 to the 19th. Times 10 to the 19th. This is the density, so this is the number of electrons per meter cubed. But what did it ask me to find? It asked me to find the average number of mobile electrons when we have 5 grams. So I have to use that to figure out the number of electrons that I have. Okay, so I have 5 grams. I want to figure out what the volume of 5 grams is. So I know that density is equal to mass divided by volume. And for the density, I think I can go to somewhere later on in the project, maybe page 14. Okay, so for germanium, they give you information on page 14, which we actually need earlier. When you answer part D on page 6, if you look on page 13, they give you the density for silicon and then some other information also. Okay, so you can either look this up or you can remember, you can find it on page 13 when you need it. Okay, so we need the density is 5.4 grams per centimeter cubed. So here I'm looking for the volume. So I have volume is equal to mass divided by density. The mass is 5 grams. The density is 5.4 grams per centimeter cubed. So this gives me 0.926 centimeters cubed. So that's the volume that I have. This is electrons per volume. So if I take this and multiply it by the volume, then I have the number of electrons, which is what I was looking for. Okay, so the number of electrons is equal to the volume times the density of conduction electrons, and the volume is 0.926 centimeters cubed. So we are going to have to convert our units here because this is centimeters cubed and this is per meter cubed. And so if I do that, I have to divide by 100 3 times. And for this, we get 2.14 times 10 to the 13th. And this is the number of electrons. So that is the answer for part A. Then for part B, it says at room temperature, determine the average number of mobile holes. Well, for the intrinsic semiconductor, the number of holes is equal to the number of electrons, so this is also 2.14 times 10 to the 13th. Okay, then you're going to answer the question in part C, and for this, if you just want to use the constant C that we had here, you can do that. So it's going to be a little bit off because you're using this, which actually depends on T, but I don't care. You can do it anyways, and just know that it's approximately, but not exactly right. Okay, and at what temperature? Okay, so here you get the information from page 13, and you basically follow what we did up here. Okay, so that brings us to page 7. We want to calculate the range of energy gaps that could produce visible light on recombination. Okay, so for visible light, we're going to say the wavelength is, let's say, from approximately 400 nanometers to 700 nanometers. Remember that for light, the energy is equal to h, Planck's constant, times the frequency, or you could say hc over lambda. So that's the energy. So then for hc, I have 1240 electron volt nanometers divided by the wavelength, and I need to do this for 400 nanometers and 700 nanometers. So when the wavelength is equal to 700 nanometers, I get E gap, that's 1240 divided by 700, that's 1.77 electron volts. And when the wavelength is equal to 400 nanometers, I get 1240 divided by 400, that's 3.1 electron volts. So the range is from 1.77 to 3.1 electron volts for the energy gaps that could produce visible light on recombination. Now for part B, we are going to consider a mole of pure semiconducting material with a gap needed to produce violet light at 400 nanometers. At room temperature, how many mobile electrons and holes are available to recombine into photons? What does this imply about making LEDs out of pure, non-doped semiconducting material? Okay, so from what we did previously, we're asked about how many mobile electrons. Okay, so we're going to use the same equation that we had before. So for the density of conduction electrons, this is equal to our constant C. This is at room temperature, so T is equal to 293 Kelvin. So we have 2.42 times 10 to the 25th electrons per meter cubed times E to the negative E gap. That's we got from up here. This is at 400 nanometers, so we have 3.1 electron volts divided by 2 times our constant K, which is 8.617 times 10 to the negative 5th electron volts per Kelvin times 293 Kelvin. And then the units here all cancel out. And we get 0.0527 electrons per meter cubed. Okay, now they told us to do this here for a pure semiconducting material. So we have information for germanium, and silicon. So if you were doing this on your own, you could just pick one of them. But since I'm doing it here, I'm going to do both of them. We had some of this information before. So remember, we looked up the density for germanium. That was 5.4 grams per centimeter cubed. If we go back to page 14, we're also going to need the 73 grams per mole, because they told us here we have a mole instead of giving us the mass. Okay, and then if we go to page 13, we can get the same information for silicon. So we have 2.4 grams per centimeter cubed, and then 28 grams per mole. Okay, now I have the density of conduction electrons. Last time, on page 6, I had to find the volume for 5 grams, and then I can multiply the volume by the density to get the number of electrons. So we're still looking for the number of electrons here. I need to find the volume, but to do that, it's going to be a little different here. So the volume is still equal to the mass over the density. So this is what we had before. Oh, I guess it's not that complicated. We have 1 mole, right? So it's 73 grams per mole, so we have 73 grams. Okay, so it is pretty much like what we had before. So we have 73 grams divided by 5.4 grams per centimeter cubed. So this gives us a volume of 13.5 centimeters cubed, or we can say 13.5 times 10 to the negative 6th meters cubed. Let's do this now for silicon. So we have the volume is equal to the mass over the density. For 1 mole, the mass is 28 grams, and the density is 2.4 grams per centimeter cubed. That gives us 11.67 centimeters cubed, which is 11.67 times 10 to the negative 6th meters cubed. Okay, so then for the number of electrons, we take the density of conduction electrons and multiply it by the volume. So the volume is 13.5 times 10 to the negative 6. The density is 0.0527. I put this in meters cubed, so the units should all work out. And we get 7.12 times 10 to the negative 6th electron. So remember the question was, at room temperature, how many mobile electrons and holes are available to recombine into photons if you have a mole? So in 1 mole, you have 7.12 times 10 to the negative 6th, which is a whole lot less than 1. So in a whole mole, you have less than 1 electron available for germanium. That's not very promising. For silicon, if we do the volume times the density, the volume is 11.67 times 10 to the negative 6th, and the density is 0.0527. This gives us 6.15 times 10 to the negative 7th electrons. This is even less promising. So what does this imply about making LEDs out of pure semiconducting material? This implies that it would not work well. Okay, so that concludes part 2. So we're going to stop here for now. You can go back and answer problem 1, part C and D on page 6 for homework. And then in our next video, we will continue with part 3.